So let's get into Module 1, Introduction to Information Storage. Our objectives for this module focus on really understanding the context for information storage and management, a little bit about what information and data are, how we've gotten to where we are today from a storage and information and storage and management perspective, and then a little teaser of some of the emerging technologies like big data, virtualization, and cloud computing, which we'll get into much more detail further on in the course. Sort of the question is, why now with ISM, or Information Storage and Management? As you've undoubtedly seen, the data around the growing amount of digital data, you sort of get an appreciation for why storage and information technology in and of itself is really a good industry to be in. Depending on the data source, it's not an understatement to call it an explosion. Some folks predict by the end of the decade that we're currently in a 44x growth in the amount of digital information. It's an interesting scenario too, because we've moved from an environment where digital data wasn't necessarily the domain of the every person, me, you. Digital data 20, 30 years ago was really more the domain of, let's say, businesses or organizations, right? That dynamic has completely changed in the on-demand, on-command world we live in now, with the emergence of devices like tablets. Obviously, laptops have been around for a while, and smartphones. The amount of digital data we create, we process, and we need for our lives and for business is absolutely unprecedented. As you think about this problem, don't forget about what they sometimes will call the ubiquitous network access. This is the very high speeds of access that we have to computer networks, whether it's in our office, our homes, wireless over our smartphones. So the device, the access the device provides, and then the use that we get out has started this circle of individuals creating data, data then being stored centrally, accessed, shared, replicated, altered, shared again. Clearly, businesses are seeing the value in this flow of information, these transactions. It's spawned an entire new way of thinking called data science, which we'll talk about a little bit in this module, which is all really around looking at information, both structured and unstructured, and trying to derive some level of intelligence and value out of it in new and sort of exciting ways. Information is clearly, when used correctly, a competitive advantage. And many businesses use information today and advanced analytics to create new business opportunities. It'd probably be helpful to start with an actual definition of data. Think of data as just really sort of the raw facts. The important sort of evolution of the last 50, 60 years is the migration from data in a physical or non-digital form to a digital form. And you see that in the slide here with the ones and the zeros. Does anybody know what you call those, zeros and ones? What sort of way of computing information, or what's that called, zeros and ones? What sort of language is that? Right, binary. So at the end of the day, all of these discussions are about zeros and ones. We'll talk about structured and unstructured data. We'll talk about storage. We'll talk about whiz-bang capabilities like server virtualization and cloud computing. But it ultimately all comes down to zeros and ones. We've all sort of in one way, shape, or form lived through this evolution over the last several decades. Clearly, with the capabilities of servers and storage and network to provide more and more power, more and more performance, more and more storable capabilities, we've seen the flow of data and the demand for data increase. As those capabilities have risen over time, the cost has come down. When I started at EMC, if you wanted a terabyte of usable storage, you were talking about a 7-figure investment from enterprise class storage. Right now we talk about commodity storage that you can buy at a retailer or online for your home that's in the terabyte capacity. So that's just an interesting example of how good engineering, good R&D have driven capabilities up and cost down. And in the process, opened this information processing power plant to all of us. Again, network access and devices for us to do stuff with. The smarter the devices, the more data we create, the more data we share, the more data we have to store. Questions or comments on what is data? There are really two types of data, and this is important for the discussion moving forward because it provides a real context of where we are today. There are two types, unstructured and structured. A good way to think of structured is anything that can fit in columns and rows. So if your data is in a spreadsheet or it's in a database and it can fit in columns and rows, generally that's a decent, okay working definition of structured data. Unstructured is pretty much everything else, from doc files to PDFs to instant messages to images to audio files to invoices. There's still structure behind those files, right? It's not just a free-for-all of zeros and ones everywhere. There's structure, but from a data perspective, they're referred to as unstructured because they don't easily fit into columns and rows. The interesting thing is the vast majority of the increase in digital data comes from unstructured. So you'll see that that's what's stressing our industry right now, coming up with really good capabilities to deal with the vast amount of unstructured data. Not just to store it and protect it, which is always important, but also how do you get some level of intelligence out of the massive volumes of unstructured data. Businesses in general are pretty good at getting value out of structured data, right? Many business applications run on databases. There's lots of intelligence around best ways to query that, parallel processing for performance. Where you're seeing a lot of growth in innovation and technology is around what to do with this unstructured data. Yes?
I have two questions. The first question is it fair to say that while the examples given of unstructured data, the data itself may not be unstructured, but the information that you find within this data is in a structured format? Say, for a contract, the information within the contract can be structured?
Absolutely.
Or can the unstructured data be put into a structured format?
Two good questions. So the first one is, just because it's unstructured doesn't mean the flow of information in that file, let's use the term file, that can still be very structured. And you see that, right? A document with a template is an indication of logical structure within the file itself. Your second question again?
The files itself, can't they be put into a more structured format?
Great point. So the question about, well, can you take unstructured files or, let's say, content within that unstructured file and put it into a more structured system? You can. There are capabilities and technologies that scrape or parse, say, text, and they take that parsed text and they drop it into a database that has structure so that they can do stuff like querying and gaining information out of that. That's a little bit more along the lines of what you would learn in our data science class, but we will talk a little bit about those capabilities. So, key points so far: digital data growing at exponential rates. EMC, a good place to be right now because of that. Two types of data, structured and unstructured. We'll kind of dance around this with unstructured, and you get into this discussion almost by happenstance, but big data is a term that came up probably about 2 years ago at this point. That's when you first started to see it come up with some frequency on searches. It was obviously a big focus of EMC last year and continues to be this year. I hate to define something by saying what it isn't, but it's really kind of the best way to define big data. Big data is data, both structured and unstructured, so don't get confused there. A lot of people immediately go to unstructured data for big data. It's both. Big data is really data that breaks your systems. A good example of that is when you create a 23 meg PowerPoint presentation and you try to email it. Email generally won't handle an attachment that large. That's at a micro level a decent example of big data. Take a million road spreadsheet. that's structured, right? I said columns and rows, so spreadsheet is columns and rows. But if it's got 1 million rows, it pretty much breaks Excel. And at that point, it's big data. So this has become a very, very interesting place to play from an information technology perspective, because you find very, very large IT shops take the folks that are involved and built their business around search. Take online retailers that are doing literally millions of transactions a day. And they're generating huge amounts of both structured and unstructured data. And then they're left with, well, what can I do with this? Can I derive some level of value out of it? And you'll find through your own personal lives that these folks are mining that data. They're performing some intelligence behind it. And depending on how connected you are and consistent in your connection, they can identify where you are in your life and recommend something for you. They can easily discover that a young woman, for an example, just got engaged, and they'll start to send her emails or Facebook posts about bridal gowns and things like that. That's commonplace today. And to think of it 10 years ago would be sort of unheard of and a little scary. Think about the car insurance company now that's putting the device in your car, and the better you drive, the lower your insurance rates gets. That's big data. That's a big data problem that they've turned into a potential solution for them as well as their customers. What big data is changing in our industry is a couple things. One, how do you store it and process it in a way that makes it real time so you can actually perform some level of intelligent analysis or predictive analytics against it, and then use that data either as a product, right? So think of marketing campaigns where you could coalesce literally millions and millions and millions of records and unstructured data and come back with very good predictors of individuals. You could then sell that as marketing data. You could also use it as a competitive advantage for your marketing programs, advertising programs. I'll talk a little bit about marketing and advertising programs as it relates to big data and data science, because it's just the easiest example to comprehend and one that we experience every day in our lives. Data science is really the accumulation of a couple of different disciplines together under one umbrella, in large part to address the big data issue. So data science combines the ability to get this information from lots of different sources. So think of legal hacking. That's kind of the first skill that's in data science. The ability to go free of charge, say, go grab a bunch of tweets. So I'm going to grab any tweet on this. This exists, actually. You can go out and say, return me all the results for any tweet that said sat on Tuesday. And you can go ahead and you can get that, right? So that's one thing that you would pull in. Perhaps you're going to do some text parsing. So you write a script or a program that looks at Facebook posts and pulls out anything about rain as another example. So data science is the skill to work with computers and gather that data, right? Then it's the ability to use parallel processing against that data because it's generally big and you want it in real time and you want it fast. So parallel processing, all that means is it takes lots and lots of operations and breaks them down into even smaller operations and scatters them across computers, sometimes called nodes. So data science is the ability to get all that information, pull it together, do some processing against it, and then ultimately where the real value is, perform analytics. Predictive or advanced analytics is sort of the most valuable element of data science. Lastly, then, it's the ability to represent that in a way that's exciting. So data scientists typically are portrayed as individuals who have a decent imagination, charisma in how they present the data, visualization techniques, etc. All that kind of wrapped together is this thing that's data science, and practicing individuals are called data scientists. If you're really interested in that technology and you have a good math and statistics background and you've got a bent for programming and scripting, we actually have a course for that. That's called Data Science and Big Data Analytics. So, any questions about big data? Excellent. So we'll get into the meat of it now, and that's storage. Storage has evolved dramatically in the 15 or so years that I've been in IT and continues to evolve. Storage can easily be defined as the place where you store data. Some common examples of those are the media cards that are in your phone or cell phone, those those little flash cards. Clearly physical media like DVDs or CDs, traditional magnetic disk drives, brown splitting platters with actuator arms and buffers and all kinds of great stuff Andre's going to walk you through later. Disk arrays are very simply collections of storage devices with intelligence and memory and other capabilities to provide redundancy and high performance. And then probably the most legacy traditional element, which they're still around, is tape, right? Physical media tape. Where's tape most seen today from an application perspective? Backups, absolutely, right? You still have reams and reams and reams and volumes and libraries of tape being created for backup, whether kept on premises, shipped off to a secure location. However, as our friends from Data Domain will tell you, with the emergence of cheaper, faster, more intelligent magnetic disk-based solutions, we've found customers and applications within the industry moving away from tape and moving more towards backup to disk-type technologies. There is an interesting evolution within storage that's been happening really for the last, I would say, 12 to 13 years. But if we take a step back even before the emergence of open systems and departmental servers, we're looking at an infrastructure, an IT environment that's quite consolidated, right? The compute systems themselves are generally all contained in one building. That's got a mainframe. That mainframe is logically partitioned out into various applications. And then business users are using those applications either very close to the data center or within earshot using terminals. The emergence of small computers and then ultimately Unix and Windows, open systems, right, created this proliferation of compute power in and outside the data center, right? So Unix systems were in the data center. They also existed within the branch office. They existed within the business department, if you will. And this sprawl of servers created a lot of benefit because it brought computing power closer to the individuals, closer to the department. But it also created inefficiency and management challenges. So say in the 80s leading into the mid to late 90s, you had really sort of two types of storage situations. You had those that were still attached to mainframes and AS400 centralized computing. And then you had those that were embedded in the server itself. So you would buy a server and you get as much storage as you would need with that server. And then if you needed more storage, you'd buy another server. That doesn't sound as smart today, right? So if I said you ran out of storage, you would today probably go buy more storage. In the 80s and the 90s, lots of times you had plenty of memory and plenty of compute power, but you would run out of storage. Therefore, you'd attach another, you'd build out another server. Another element of this was server farms. You've heard that sort of term, or islands of servers. So the architecture was really to create the servers with the embedded storage to support a specific application or a specific unit. So as I mentioned, this created some inefficiency. So you had a lot of extra CPU, processing power, memory, fast access to storing information, and in some cases storage because these were individual islands of servers or individual islands of information. So what started to happen was the legacy benefits of mainframe, of having everything consolidated, managed logically, accessed remotely, started to happen within the traditional open systems and Windows environments through a couple of technology innovations. One was intelligent storage arrays, so collections of disks all consolidated together with intelligent capabilities and fast memory or cache put in front of it. That's one, intelligent arrays. Two was the ability to connect them efficiently through a storage network. So even in the late 90s, you were still tied to this distance limitation. You had a copper cable called a SCSI cable that would connect the storage array to the server. But copper can only go so far before the signal starts to attenuate. So you're left with a handful of meters. That was a problem, especially as we wanted to get our arms around the departmental servers that might be 7 stories up or in another location of the campus. So the emergence of fiber optic cable and protocols specific to storage running over that fiber optic cable allowed us to connect more servers together to a single storage device or collection of storage arrays and do it over longer and longer distances. That's what then started this sort of evolution or revolution within the storage industry to reconsolidate, gain more efficiency, get a better handle on management, and in the process do a better job with performance and availability. Sort of the let's put all our eggs in one basket argument, which typically isn't a good idea, is a good idea if it's the best basket and the basket that never tips over, breaks, or fails. So that's sort of the current evolution of the storage architecture. Now, what we'll talk a little bit about later is how virtualization and now cloud computing is really unlocking the power of that consolidated environment. As we consolidated in, say, early 2000s, there were still some inherent issues around the sharing of those resources in a flexible way. Virtualization is starting to overcome some of those challenges. Any experiences or questions about this evolution? Okay. I may have mentioned this term a couple of times. So data center, very simply the physical facility with the components inside that provide the information processing capabilities and power. So it's the physical facility itself, the logical and physical elements of it, as well as the things that you would need like power and cooling. Right? Today, power and cooling is a very big deal because of the cost of energy. Typically look at 5 pillars within the data center. And I'll work bottom up because I'll work from the core of the data center out. At its core is storage, right? That's ultimately where the zeros and ones of the data ends up. It moves through the data center and outside the data center through network. We'll talk probably about 2 types mostly. The storage network piece, which can be 4 or 5 different choices of protocols and standards. Andre and others will get into that. And then in terms of access, sometimes within the data center, certainly outside the data center, you'll talk about your traditional Ethernet IP-based networks. Host or compute is really the pillar that talks about, sometimes we call it the server. Right? I like host and compute better because it's a little bit more of a generic term. But this is where the numbers are being crunched. Think of it that way. If it's all about zeros and ones, the host and compute is where the zeros and ones are ultimately, the most of the processing is happening. That's where on any host or compute you have an operating system that's controlling the CPU and the memory and the traffic in and out. So on top of that operating system will sit one of 2 things or both. Some sort of structured way to manage the zeros and ones like a database. You'll sometimes see RDBMS, which is Relational Database Management System. And then either natively on the operating system or on top of the database will be the application. And we all know what apps are now because of smartphones. Even my dad and my mom know what apps are now because of smartphones. But this could be email. This could be an email application, transaction processing, web serving. Whatever the software is that's providing the ultimate capability is the application. Obviously, these all have to work in concert together. The better they work together, the more powerful the IT solution is. Questions about a data center or the 5 pillars? Yes, sir.
So the DBMS, is that like a Hyper-V or something like that? Is that would that be a DBMS?
So good question. So the hypervisor or Hyper-V sort of layer, which is the key element of how you virtualize servers, is not actually in the DBMS level. It's part of host or compute. So for those of you who aren't familiar with what a hypervisor is, we'll get into that later, but very quickly, as you consolidate IT resources, one of the ways in which you unlock the power of those consolidated resources is to virtualize the server environment. So remember when I was talking about the traditional islands of information and servers? One of the problems that created is underutilized CPU and memory. Server virtualization, what's a very popular version of server virtualization? VMware, right? VMware's got a great solution. That allows you to take that physical box and actually carve it into multiple logical boxes, or they call them virtual machines. The hypervisor sits really actually under the operating system in sort of the bare metal version of a virtualization solution, and for which then the operating system is built upon and then virtualized. So what's a good example of a database system? There's several popular ones. Does anybody know one? Oracle, right? The core Oracle product from decades ago is a relational database, right? That creates tables and log files and allows you basically to put in the zeros and ones, create records, query them, all those good sorts of things. SQL Server, MySQL, Informix, all examples of database systems. But keep in the back of your mind the 5 pillars. It's good to sort of ground yourself as you're navigating through the physical or logical data center. So what element of the pillar am I talking about, and why is it relevant, and what are sort of the flows around it? And hopefully at the end of this course you'll have a really good sort of mental picture of these pillars and how they work together with a real more acute sort of understanding of storage. As an example of a data center and how the elements are working together, we have an order transaction system example. So a client going over a local area network or a wide area network, I would dare to say maybe even the web at this point. They're seeing some sort of order form, website, they're putting in some data. All that transaction that I just described is really being governed by the host or the compute layer, whether it's a physical or a virtualized system. That is then, in most cases now today, talking through a storage network connection, either fiber channel, iSCSI, fiber channel over Ethernet. These are all technologies that we'll define in much greater depth as we go through the course. A couple of options that are available into the intelligent storage array. So you see a good graphical depiction of the storage array. To the back, you see the gray cylinders. Those are the magnetic disks. You see sort of a grid which represents cache or fast memory. And then you have other components, cables, microprocessors. The more intelligent the storage array, typically you'll find the faster the performance, the more features and capabilities that are there. One thing that I didn't mention in the evolution is storage arrays have become much more intelligent over time. The capabilities that storage arrays now have to move data around, either for performance or replication or recovery capabilities, is unbelievable given where we were 10 years ago. So you'll talk a lot about the movement of data when we get into both the business continuity and the virtualization discussions. So the data flows from the client through the host compute down to the storage array. As it's written, as they say, to the disk, that's the process of marking the zeros and ones on the disk. Or if the information is required on the other side from the client, that's called a write, where a read, excuse me, where you're reading the data, the zeros and ones, off the disk or out of the memory or cache, as they say, in the storage array, and then back through the host compute where it gets crunched and manipulated in some way, back out ultimately to the client. So in addition to the 5 pillars, you now have the sort of the other side of the coin. The pillars are sort of the elements. You also have to look at the characteristics of a highly performing data center. And these are all the things that you would want in your information technology processing capabilities. We could start up with data integrity. That's a given. That's one that's really not negotiable. What you put in for zeros and ones, you have to guarantee comes out of the data center, out of the individual component within the data center. These are where things like error correction codes and other intelligent logical algorithms that ensure that the zeros and ones that come in are the zeros and ones that come out. Integrity is a key element. It's sort of the minimum bet at the table, as they say. Availability is really around access to information. So put integrity aside for a bit. This is about beyond command on demand. When we want information, we have access to it. Availability quickly gets into the business continuity discussions because anything that's mechanical or physical can ultimately fail. So you'll see in intelligent storage arrays and in good data centers what they call redundancy built in. So that's typical multiple components or components that can fail over for one another, either in an individual piece like a storage array or in a larger capacity within the data center. So when you hear of like a hot site or a disaster recovery site, that's typically another data center somewhere else connected to your primary that can come up online, either all of it or components, if something fails, either for whatever reason, natural causes, natural disaster, security breaches, etc. So security is the other one. As we go more and more into the virtualized and cloud environment, security was always important. It's now gotten right to the top of the list. So if you ask CIOs what's your biggest issue, Once they get past cost and I spend too much of my budget to keep the lights on and all those good things, they'll get down to, well, I want to do virtualization and cloud because the capital and operating cost savings are unbelievable, but I'm concerned that as I start to put all my information in one piece, right, in one private cloud, as they say, or if I push it out on the public cloud, how can I ensure that information, my transactions, my customer records are secure? So security is not only about physical security into the data center, right? It's about the security of the information as it moves throughout the logical and physical elements of the data center. Capacity is a huge one, and it's big and important because that's the biggest problem that we face in our industry is the massive growth of digital information, digital data. So the ability to kind of deal with all the requirements as they come in. The interesting thing is I said earlier that it's mostly individuals now that are creating data, right? But whose responsibility is it to manage, store, and protect it? Roughly 3/4 is the responsibility of an organization. So take a simple example like, do you use public email or publicly free available email outside your corporate email? Right? I use Hotmail. My wife uses Gmail. If you think about where all that data is stored, right? You create it. You use it. So I'm the individual creating that. But Microsoft or Google or Comcast or whomever that's providing that email service is ultimately the one that's storing all of that information. Obviously, if you right-click, save the attachment locally, now you've got it locally. But in general, all of those emails are stored by an organization, right? So the capacity problem is a very big deal. And it's why technology like deduplication, compression, are important, as well as consolidation and virtualization, so that you are absolutely optimizing to whatever extent possible your utilization. Scalability has always been an issue, but people normally think of scalability in terms of I got to scale up, right? I constantly have to scale up. What we've learned through virtualization and cloud computing, that the ability to scale down is important too. So think of a popular online retailer come holiday time. They need to be able to scale out their online transaction processing or web ordering system very, very quickly. But if they were to build their environment to peak, they'd have a lot of unutilized capacity, memory, CPU, data center. They'd have a lot of that for the slower seasons, the non-holiday seasons, just sitting around. So the ability to scale up and scale down is very, very important in today's data center and becomes more important moving forward. So we'll explore technologies in terms of virtualization that allow you to do that, and private and public cloud computing models that will allow you to do it. And lastly, in one shape or form, we all have some sort of technology bent in us, and technology folks ultimately have to have something to say about performance, right? If it's not bigger, faster, badder, then we probably don't like it. However, what we've learned about performance is performance can scale with the application. It can scale with the user. So another beauty of the virtualized and cloud environment is the ability to have sort of varying levels of performance that make sense, that use the resources that you want to use when you want to use them. So generally we think about these things as, oh, I need the utmost in all of them. Well, for integrity you do. For the other ones, I think it's about looking at the application or the user requirement and scaling these requirements sort of up and down as it makes sense. And one way to do that is virtualization and cloud. Please.
About scalability.
Yes, sir, please.
You mentioned about scale up and down. With Isilon, there is new concept of scale out also.
Yes. So the gentleman here is mentioning the idea of scale out. So we've talked about scale up is traditionally what we've done with storage, which is you continue to offer larger amounts of memory and storage and scale up performance. With our recent acquisition, well, it's not so recent anymore, of Isilon, and we'll cover this in the class, there's this idea of scale out NAS, which is the capability essentially to just keep adding nodes to the cluster and get larger and larger file systems. That's the Isilon use case. So you can have millions and millions and millions of files within these very, very, very large file systems. So the idea of scale out, not so focused on, let's say, more focused on providing very large big data file system type capabilities as opposed to, let's say, scaling up the highest levels of performance for, say, a Wall Street transaction processing type application. Within the data center, and you think about management, I want you to focus on three things. The continuous monitoring of the data center, right? So these are the professionals sitting in the operations center, sometimes referred to as the NOC, the Network Operations Center. And they're basically watching things, looking for lights to flash and signals and indications to say that we either have had a component fail, we've had a performance issue, we've had a security breach. Reporting, the more you move into a cloud environment, the more you have to keep track of usage, access, so that you can account for the services that you're providing and potentially even charge somebody for those services. Reporting's always been important in the data center, but today's environment, today's implementations make reporting even more and more important. Provisioning is simply the act of taking a resource and giving it either to an application, a user, etc. These have historically been provisioning, very manual tasks. Occasionally, you would script them to take some of the steps involved and make them automated. With virtualization and cloud, provisioning, one of the very first things and the very first benefits is to start to orchestrate and automate the provisioning so that if somebody wants 500 gigabytes of storage and they press OK, that it actually happens in the background without a person having to use a GUI application or write in a command to, let's say, provision a RAID group, put LUNs on top of it, put security access associated with that LUNs. All of that stuff happens in an orchestrated and automated way in a virtualized and cloud environment. So one of the most immediate benefits of cloud, virtualization even, is the elimination of some of the more rote manual tasks that typically fall under that provisioning sort of capability. So when folks get nervous in the data center about where does my job go once we virtualize, once we get cloud, typically there's no shortage of work to be done. And what cloud can help to do is minimize the more rote manual tasks and open up your time and your thinking for new lines of business, service models, being more proactive, being more of a business partner, those sorts of things. So I think cloud and virtualization actually tell a really good story for the folks that are in the data center today about a more exciting future in terms of their jobs or careers, et cetera. At a very high level, and we'll go into more detail on this later on in the class, virtualization is simply the ability to take physical resources and logically abstract them. The common example that everybody can typically relate to, or one of two common examples, is the VMware example. So that's think of a physical server, either in a cabinet or a blade server, that's got, what does it have in it? Well, it's got lots of memory, right? Lots of RAM, it's got CPU power, typically has some level of internal storage. Virtualization is the capability to partition, if you will, those resources into multiple servers, typically referred to as virtual machines. So when you talk about virtualization, you'll hear terms like pools and resources and automation and orchestration. The value of physically taking the physical resources and abstracting them virtually is what? What is the value of that? I've mentioned it a couple of times, but it's worth reiterating. Why would you do that? Why would you take efficiency is one reason, right? One physical server that becomes 4 allows you hopefully to use more of the CPU, more of the memory, and internal storage if that's there and capable. What other reasons?
Cost savings.
Cost savings, right, tied to efficiency. The ability to continue to max out your physical machines through virtual machines may avoid purchasing of new machines, absolutely. Any other reasons to virtualize? Easier to manage. Talk a little bit more about that, and if you could, do the push to talk as well on the microphone so we can hear you.
It would be easy to manage because in virtualization, most of the times you have some console or management client that you can just go set up provision, memory, CPU, any resources. You don't need to go and build and install OS. we can make a template, and template just installs within maybe 2 minutes instead of sitting half an hour.
Absolutely. So regardless of the virtualization vendor of choice that you choose, almost all of them have very good tools to quickly and rapidly deploy virtual machines, templates, workflows. So it makes management that much easier, certainly. Any other comments or questions around virtualization? Obviously, one slide, high-level overview. More to come, though. Virtualization on the journey leads us to cloud. So virtualization, in my mind, is sort of a means to an end. Cloud is more the end. Not the end in and of itself, but certainly an end from a computing perspective. Cloud is really about delivering service. That's really what cloud is. It's the combination of the underlying technology, the infrastructure, the software, and then some business rationalization against it to provide a service. Lots of easy examples of cloud computing-based services. I mentioned one earlier. So public email is a good cloud implementation. You can get a free Gmail or Hotmail account literally in seconds. And that's provided to you as a service. In the case of Hotmail or the free Gmail, it's a freemium service, right? It doesn't cost you anything. But there's also the premium version of that, which you can, for more services, you can roll out your credit card or some other form of payment, and you can get higher performance, more storage, higher availability against that email account. We've seen a large shift in the last probably half decade to doing customer relationship management through the cloud. So a couple of popular vendors there, one dominant vendor that allows you basically to do your sales customer sort of relationship management stuff in the cloud. What does that mean? That means you don't have the physical hardware in your environment. You're not actually storing the data in your environment in a public cloud implementation. The hardware, the data center, is owned by another company, and you basically, and all your employees, through an interface, access via the web to get to that. And that's where the customer's information goes, and then you pull it out as required. So that allows you to basically pay as you go, right? You have a license model that makes sense for your utilization, as opposed to, as I mentioned earlier, you build out to what you think your peak or your scale is with capital and operating expense, and then hopefully use that or maybe not. So public cloud is where you're basically, as a business, relying on another business through the web or over a network to provide that data center capability for you. And in any relationship, you're going to want some level of service associated with it. Private cloud, on the other hand, is where you generally own that infrastructure yourself. You're building out that service delivery capability, but you're offering it to your own users, your own business constituents, as opposed to, in my example where I use the Hotmail, you could definitely have a cloud version of Exchange within EMC, but that hardware and the people managing that hardware and the data center is within EMC's direct control. Couple key things around cloud. For it to be cloud, if you use the National Institute of Standard and Technologies, or NIST definition, which you'll see later in the class, a couple of key characteristics that it has to have. You've got to have the sort of the ubiquitous network access for it to be cloud. It's got to be accessible pretty much anywhere, anytime. It's got to be self-service in nature for it to be cloud. For it to truly be cloud, it can't require a bunch of forms and sign-off and such. You've got to be able to go request it, and in a responsible amount of time, kind of get it back. It also has to be metered, which is the idea of tracking usage, whether that's CPU usage, whether that's memory usage, whether that's storage usage, or even application usage. Tracking that quite maniacally so that you can charge it back, either for real cost, in the case of, say, premium Gmail. You're actually going to pay money to Google, so they've got to track your usage so that you can square up that relationship. Or if it's internally, right, then it may be an internal cross-charge. I pay out of my cost center roughly $300 a month for a series of virtual machines so that we can run our training, project tracking application on virtual machines, because we have folks developing training here, we have them in Bangalore, we have them in North Carolina, we have them in Colorado, we have them everywhere. And we have to track the hundreds of projects that we have going on at any point in time. So to do that, we've invested in virtual machine technology. So we've gone through our own EMC IT department, and they've said, okay, for this level of compute power, for this level of memory, and for this amount of storage, and these levels of availability and continuity, it's going to cost you about $300 a month. So that gets billed against my cost center every month. That's an example of a private cloud sort of situation with internal chargeback or chargeback, excuse me. Lots more to come about cloud, but just a teaser at this point. It's kind of the sort of where we are in the evolution now is really cloud. If you don't have any other questions, I will tell you that we've been tracking some data about how customers and non-EMC users use storage for the past 6 years running. This is the 6th year. And virtualization in cloud is proving out in the data. The amount of usable attached capacity that is now with either virtualized servers or in the cloud has gone up dramatically, like we've never seen before. So in the next couple of years, expect, by the end of this year actually, expect us to cross the point where more usable capacity is with virtualized servers in cloud than in classic technologies, classic environments, which you'll go through. So we've, like I said, been collecting this data for about 6 years. We saw the emergence of iSCSI and some of the IP SAN technologies. We saw adoption associated with that. Never seen anything like the adoption of virtualization in cloud, at least from a storage capacity. So it's certainly worth our attention. It's worth our learnings. Covered a fair bit of territory. Again, this is all about context. This is so when you get into the guts of the storage array or what a clone versus a real-time copy is, when you get into all those discussions, have in the back of your mind, at the end of the day, it's all about information. Big data and data science is an interesting new discipline within that information. Storage architectures and data centers are in evolution. We're at a very interesting point in that evolution now. Remember the 5 key elements of the data center: applications, compute, database, storage, and network. Remember all the abilities, right? Availability, scalability, performance. Those are sort of the key characteristics that really set the context for virtualization and cloud. They're service management disciplines, really. And then lastly, the exciting bit around taking the physical infrastructure of the data center and virtualizing it for efficiency, for performance, for flexibility. And then the ultimate thing that everybody's chasing today is a cloud-based environment that allows you to efficiently use the resources, track them, charge them, scale in, scale out as your customer or your business partner requires. Comments or questions on Module 1? Yes, sir.
Going back to the core of the data center example, how many applications would you say are attached to one host or compute and storage network?
Sure. The question is typically how many applications are connected to a single compute or storage. So traditionally, servers were dedicated to applications. I hate to generalize because you really can't. Every environment's different. But if I had to generalize, I would say that servers or farms or collections of servers were dedicated to applications. So you'd have that's my set of AIX servers over there that are doing my casino accounting, right? That's my HPU Xboxes over there that are running my hotel software. Those are my Windows boxes that are running my Exchange. Now, in some situations, those had internal storage. That's probably 10, 15 years ago. In other cases, those, let's take the AIX example, those were then connected to a storage network to an array. So now my casino accounting applications on AIX boxes that's connected to an intelligent array, and that array is doing lots of interesting things. It's copying the data. Maybe I've got a disaster recovery site. So generally, that's the way it would work. Now, in today's virtualized environment, it's all up in the air. You'll get a situation where you might have 10 blade servers in a rack, right? And on that could literally be 15,000 virtual machines. And that's hosting all of your, let's say, business critical applications. So it very much varies, But I would say from the historical perspective, and as you get into the data center, as you're working on your own applications or you're working with customers, one of their big challenges in moving to the cloud is actually an inventory of all their existing applications. So getting that list of 100 or 1,000 applications and the architectures behind them, picking out the right candidates to first virtualize and then ultimately move to a cloud environment, that's where you see a lot of the inertia. So I said that the rate of adoption for virtualization in cloud is quite high. It is, but there's still a level of hesitancy. And a lot of it is about, well, this thing's been working for 12 or 13 years quite well. Now I'm out of maintenance or I'm paying too much in maintenance. I got to get off it. But so doing that work is typically one of the big challenges, because unless you get to the cloud environment, you're typically spending 3/4 of your budget just maintaining what you have today from an IT perspective. And that's just not the capital dollars. I equate that a lot to sort of the mind share of the people, right? So if you look at your organization, 3/4 of your organization is just worried about keeping the lights on, as they say. Other questions, comments? Please.
Yes, I have an additional question. From a performance standpoint, say you have a host or compute that's connected to a separate storage array.
Mm-hmm.
When we talk about a client user trying to access the data,
Mm-hmm.
is when there's issues with accessing that data with the performance or the time that it takes, does those issues usually occur as a result of the storage array or as a result of the host compute?
Performance issues can come up across the board, right? You could have intermittent network access from the client to the compute. You could have an oversubscription of traffic and activity within the compute. You could have you could have some sort of flood of activity down at the storage array. Most of the enterprise class computing and storage arrays have enough redundancy built in and enough fail-safe features that unless something seriously goes wrong at peak workload times, performance is generally kept within acceptable levels, right? It's tough to pinpoint any one component and say that one component is more likely to fail than another. But one of the beauties of virtualization is the ability to put with a physical server that you then virtualized, you have the capability to throttle resources against virtual machines and certain sizes and throttle file sizes, so that one very resource-intensive user or application doesn't flood the entire physical set of resources. I actually think that problem, it's a problem that you have to solve with virtualization, but once you solve it, I actually think it works out better than in your traditional or classic environment. Because if you do have a mission-critical application that really needs more resources, it's got a place to go, right? It's not locked into its own physical server or its own storage in a purely virtualized environment.